The next application that I would like to do is thinking about gravity and the Earth. So I really like this example, and it hopefully helps you think through a few misconceptions about Newton's third law and force pairs. So first we'll talk through it conceptually, and then we'll actually do out the math on the next slide. So the first thing to think through is that if we have a ball near the Earth, that we know you have the force of the Earth on the ball, which we usually just call F sub g. But Newton's third law says the ball should be pulling up equally hard on the Earth, right? So if the Earth exerts a gravitational force on the ball, then the ball must exert a gravitational force on the Earth. And part of why I always stress that it's the same type is that these are both gravitational forces. It isn't that the opposite force is a frictional force, or sorry, the Newton's third law force is not a normal force, it's not a frictional force, it must also be a gravitational force. So if we have the Earth exerting a gravitational force on the ball exerts a gravitational force on the Earth. We know that the ball accelerates downwards at g, and this has been discussed in a previous section of videos talking about the difference between mass and gravitational force and weight. So we know that the acceleration of the ball is going to equal g, and we usually call this in the negative y hat direction, right? So what's going on with the acceleration of the Earth? It should have we see the equal and opposite force, but does the Earth accelerate upwards at g? Certainly that is not our lived experience. And while sometimes our lived experience does bring with it misconceptions, ideally physics is not telling us that the world around us is not at all true. Like physics should more or less be agreeing with our real world experience as long as we're accounting for everything such as friction. So let's go through the math and try to understand what acceleration the Earth has, given that we've said these forces are equal and that we know what acceleration the ball has. From Newton's third law, we know that the force has its pairwise force, so the Newton's third law pair, is the same magnitude in the opposite direction. So ball on Earth, agent on object, Earth on ball is reversed. Earth is now the agent, ball is now the object. And that minus sign says just flip the direction around, and in this case the magnitudes are equal. So this is a very valid equation to write vector-wise. Now we know one of these. We know that the ball on the Earth is then negative Earth on ball. And we've said that the force, well, we know the acceleration, but the force of the Earth on ball is going to be m ball, so that's just the mass of the ball, times g in the negative y hat direction. So the reason we get to the plus sign is that we had a minus here and a minus there. So this minus times that minus gets us to a plus. So the ball on the Earth would provide a force of the mass of the ball times gravity in the upwards direction. Plus y hat just means up. So now we can use Newton's second law. So this first equation was basically coming from the third law. And now we're using the second law. And the second law says that we can take our force, and in this case, this is the only force we're considering, so it is equal to the net force. And we can say that the magnitude of this, right, I'm going to now consider this a one-dimensional problem. We don't have to worry about the direction since this is the only force we're thinking about, 1D. F equals ma. So this is now the mass of the Earth, since the Earth was our object. So we're now talking about the mass of the Earth and the acceleration of the Earth. But we've also brought this down from before. So this is coming from Newton's third law. I've kind of flipped it around. So we're saying mass times acceleration equals net force. This is the only force we're worried about, and we know its magnitude from the first part. So the goal is to solve for this. So we divide out mass Earth, and so we now have the mass of the ball divided by the mass of the Earth multiplied by g. And this is a nice moment to check your units. that both of these are masses. So if both of them are in kilograms, the kilograms cancel, and we know that g is an acceleration. We write it as 9.8 meters per second squared. So we're left with the correct units for acceleration. So that's good. So we have to actually assume a mass of the ball here. The mass of the Earth is something you can look up either online or in the front cover of your book. But what's a reasonable mass of the ball? We have to actually assume something here. Let's pick 1 kilogram. That's pretty heavy ball. That's not a ping pong ball or a tennis ball, but 1 kilogram could be the mass of a ball. So if we plug in 1 kilogram for the mass of the ball, and the mass of the Earth is 5.98 times 10 to the 24 kilograms, it's a big number because the Earth is big, and we then multiply it by our acceleration. We now get a very, very small acceleration. Look how small that is. So it's in fact true that every time you throw a ball up, and if you're capable of throwing up a 1 kilogram ball, good for you. So if you throw up a 1 kilogram ball, it accelerates downwards at g, 9.8 meters per second square. It is also true that the Earth accelerates upwards at this tiny, tiny, tiny acceleration. And this makes sense because there's a ton of things all over the Earth that are going up and down all of the time. And you imagine that the Earth isn't jiggling back and forth all the time, right? It isn't that throwing a ball up causes an earthquake in Australia or anything. So we get a very small acceleration of the Earth, and the reason for that is because of the mass of the Earth is big. So I hope that you remember this for 2 reasons. One, to remember that every force occurs in a pair of forces, a Newton's third law pair. So even the force of gravity, there is an equal and opposite force acting on the Earth. But we don't worry about it since we don't consider the Earth in our system. The second thing that I want you to remember from this is that even if you have equal and opposite forces, the accelerations you get are different because the masses are different. Where this is going to matter is if we talk about collisions, if we talk about one object pushing another. In that case, and we'll talk about this, we talked about this with the blocks, that if we know that the accelerations are the same, we say that the net forces must be different. So it's really important to recognize that there are some situations where we say the accelerations are the same, but since the masses are different, the net forces must be different. And in these situations, we say that we know that individual pairs of forces are equal and opposite, but the accelerations might be really different, even if those were our only forces, because the masses are very different. So that distinction between acceleration and force due to mass is really important, and hopefully this is one way to remember that.